Okay, so in the last video, we started talking about the first derivative test, which essentially helps you find where the local min and max of a function is using the first derivative. So just to review, when we use the first derivative test, first we find f prime of x, then we find all x's such that your first derivative is equal to 0, because remember, that's when f prime of x switches signs, potentially. Then we test the values. This is your critical value. The x's that make your derivative 0 is your critical values. Test x values before and after critical values to see if your derivative switched signs, meaning your slope went from increasing to decreasing or decreasing to increasing, meaning you had a min or a max. So let's try it with an example here. Let's do f of x equals 5x cubed minus 3x squared plus 4x. Okay, let's find our derivative, which is 15x squared minus 6x plus 4. We set it equal to 0 because that's when our derivative potentially switches sign. So we can use the quadratic formula to solve the x's for the x's here. So remember, your zeros are when you have negative b plus or minus b squared minus 4ac, and that's the square root of that, all over 2a. So let's just plug in values. Here's your b, negative 6. So negative 6 plus or minus b squared is 36 minus 4 times a. Here's a, and here's c. A is 15, c is 4, and all over 2 times 15. So let's simplify it. It becomes 6 plus or minus the square root of 36 minus 15 times 4 times 4 is 240 all over 30. This becomes an imaginary number right here, so you don't have any zeros. You don't have a max or min, because you can't take the square root of a negative number. So let's try a different function to test out. Let's try f of x equals 3x cubed plus 4x squared. Let's see where the local min and max are of this function. So f prime in this case is 9x squared plus 8x. Okay, we want to know when this derivative is equal to 0. You can see both share an x, so you can factor on an x. You're left with x times 9x plus 8. This whole thing becomes 0 when either x is 0 or when 9x plus 8 is 0, because anything times 0 is 0. So this becomes 0 when x is equal to 0 or when 9x plus 8 equals 0, which is when x is equal to negative 8 over 9. So you have two critical values, x equals 0 and x equals negative 8 over 9. We want to know what happens at those critical values, at 0, at negative 8 over 9. Okay? Does f prime switch signs at those critical values? Okay, so we're looking at f prime of x. So let's look at a value before negative 8 over 9, which is negative 1. So f prime of negative 1 is equal to 9 times 1 squared plus 8 times 1, negative 1. 8 times negative 1 is equal to 9 minus 8, which is 1. That's a positive number. We want to know what happens after negative 8 over 9. Let's say negative 1/2. So f prime of negative 1/2 is equal to 9 times negative 1/2 squared plus 8 times negative 1/2 equals 9 times 1/4 minus 4, which is a negative number. So it's a negative right here. And then lastly, what happens after 0? So let's pick 1. F prime of 1 is equal to 9 times 1 squared plus 8 times 1 equals 17, which is a positive number. So indeed, we switch signs. At negative 8 over 9, we go from positive slope to negative slope, so it's a max. At 0, we go from negative slope to positive slope, so that's a min. So we have a local max at x equals negative 8 over 9. To find the y value, we need to find f of x, which is equal to 3x cubed plus 4x squared. Okay, this is equal to, let's see, 8 times 8 times 8, 512 over 9 times 9 times 9 is 729 times 3 plus 64 over 81 times 4 becomes 512 times 3 divided by 729. So negative 1536 over 729 plus 4 times 64 over 81. Okay. You can plug this into your calculator to get an approximate answer. So we've got negative 1536 over 729 plus 256 over 81, which is approximately 1.053. So we have a local max at x equals negative 89, 1.053. Our local min is at x equals 0, which f of 0 happens to be 3 times 0 cubed plus 4 times 0 squared, which is just 0. So we have a local min at 0, 0. Okay? So you find out when your derivative becomes 0, see if it switches signs, and that tells you whether you have a max or a min. So that's the first derivative test. Now we can talk about the second derivative test, which tells you whether your function has a point of inflection. Okay? So a point of inflection, if you remember, is when your function changes concavity. Meaning you go from speeding up to slowing down. So speeding up to slowing down, accelerating to decelerating, or vice versa, slowing down to speeding up. So when your function is concave up, f prime is increasing because your speeds are getting bigger. Meaning f double prime, which is the slope of f prime. So f double prime is the slope of f prime. So if f prime is increasing, its slope is positive. Similarly, when f of x is concave down, f prime of x is decreasing, and f double prime is negative. So you can use this to figure out when you have a point of inflection. Your point of inflection happens when your second derivative switches sign. Okay? And obviously, in order for it to switch sign, f double prime has to first hit the x-axis. So we can do like a quick picture of what that looks like. Okay? So let's say we have f of x. And let's say it switches concavity here at 3. So first it's concave up, and right here at 3 it becomes concave. So concave up, like speeds are getting bigger, then suddenly it becomes concave down. What happens with your f prime of x is first you're speeding up. So your speeds are getting bigger. Okay, so your speeds are negative but getting bigger. And then at some point, they start getting smaller again. Okay? So then what happens to your f double prime? Your slopes are first positive. As you can see, your slope here is positive. And then suddenly it hits 0, so your slope here is 0, and you become negative. So there's a switching from your positive to negative. So we can analyze this using the function. So obviously we can see graphically what's happening, but we can analyze your function f double prime to see what happens to f, what happens to the concavity of f without graphing. So let's do an example. Let's say we just do a simple function, f of x equals x squared plus 3x cubed. We want to know when this function is, what the points of inflection of this function is. So really quickly, we can find f prime, which is 2x plus 9x squared. F double prime is equal to 2 plus 18x. We want to know when this switches signs. So we know it switches signs if it crosses 0, the x-axis. So we have 18x equals negative 2. X equals negative 2 over 18, which is negative 1/9. We want to know if it switches signs at negative 1/9. So we want to know if f double prime is before, which we can use negative 1. So f of double prime of negative 1 is 2 plus 18 times negative 1, which is negative 16. And then we want to know what happens after. So let's pick 0. F double prime of 0 is equal to 2 plus 18 times 0, which is 2. It's a positive number. So yes, we do switch signs. We go from a positive slope to a negative slope. So our f prime is increasing, decreasing. This is f prime. Meaning f goes from concave up to concave down. Okay, so this is how you use the second derivative test to see if you have a point of inflection. Obviously, your point of inflection is at negative 1/9, but to know what the x value is, you have to plug it back into your original function. So f of negative 1/9 is equal to negative 1/9 squared plus 3 times negative 1/9 cubed, which is equal to 1 over 81 plus 3 times negative 1 over 9 times 1 times 9, which is equal to 729. We add these together, we get 9 minus 3 all over 729, which is 6 over 729. So you negative 1/9, 6 over 729 is your point of inflection. Okay? So that's how you use the first and second derivative test. You can practice with functions to see how to apply these. So here's some functions you can practice with. Find the local min and max and points of inflection of these functions. So f of x equals 4x squared plus 1/2 x minus 3. F of x is equal to 1 over 2x plus 3x cubed, and 3. F of x equals x minus 4 plus root x. So try to see where the local min, local max, and points of inflection are for these functions using the first and second derivative test.